Hello, my name is Andrew VanderZaag. I'm a research scientist with Agriculture and Agri-Food Canada in Ottawa, and I'm going to be speaking about emissions from biogas and digestate in Canada. So we know that biogas has several benefits environmentally. We can produce energy and heat that displaces fossil fuels. The digestate has higher fertilizer efficacy in the fields. We can reduce greenhouse gas emissions, decrease odors from the manure, reduce pathogens and weed seeds because of the heat in the digestion process, and recycling wastes from other sectors, and displacing fossil fuels. But a question we have asked is, how does biogas change the emissions? We know that in a conventional livestock system, the manure needs to be stored until it's the right time to apply it to the crops. And while the manure is stored, there's anaerobic conditions in liquid tanks that produces methane and ammonia because of the availability of nitrogen. And when that manure is applied to the fields, there's also ammonia again and nitrous oxide emissions. Nitrous oxide, of course, has a very high global warming potential, and so we're interested in all of these gases. And when a farm installs an anaerobic digester, we want to know, are there any emissions directly from the digester of methane? Are there emissions of methane or ammonia from the digestate storage? And what about from the soil and the crops? So in some studies we did in Canada, we've seen some typical values that look like this. For a normal dairy manure, we have the data here in the middle column, and for digestate from the same farm, we have the data on the right column. What we see is an increase in the pH, and we see an increase in the mineral nitrogen, and we see a decrease in carbon. It makes sense that carbon would be decreased because the point of the digester is to collect carbon and use it for energy in the form of methane. And one of the reasons in Canada why the carbon is not reduced more is because many of the digesters are not only using manure but also co-feedstocks, other materials from food processing, for example, fat, oils, grease, things like that. So we did a laboratory study to look at the effects on methane. What we saw over a long time of incubation was that methane emissions from the digestate, the potential for producing methane was lower than the potential for producing methane from the manure. And that is the potential per kilogram of volatile solids, or what's called in the IPCC the B naught. So there's a reduction of the B naught by about 32%, and there's also at least 40% reduction in volatile solids, sometimes much higher. And so overall, we get a big reduction in the methane potential, in the amount of methane that would be emitted from the digestate. And then we did quite a few dairy farm scale studies, and we wanted to compare different technologies. Farms with or without biodigesters, farms with or without a screw press, which is this machine, separates the solids from the liquids, and farms with or without nutrient recovery. And I'll talk about each of these next. First, we looked at the facility emissions. What are the fugitive emissions from these systems? Here's an example. We use open path lasers to measure methane concentration in the air, downwind and upwind of the facility. And we observed these the green circles here. Under normal conditions, These are the methane emissions from the whole facility, but sometimes get very high methane. And those times relate to leaks from the facility through venting and sometimes through flaring, even if the flare is not working correctly. But most of the time, the emissions are low, and some facilities have very little leakage because of the way they're designed. Other facilities seem to have higher leakage. So it's important to design the systems for low leakage and to have consistent feedstock to maintain stable gas production. And then we did studies with the same sensors to look at digestate emissions for methane and ammonia. And this involves using a laser sensor upwind to measure the concentration of methane or ammonia upwind, and downwind to measure the downwind concentration, and then using an anemometer to measure the wind speed, direction, and turbulence, and combine it with a WindTrax model, we can get an estimate of the emission rate from the digestate for methane or ammonia, depending on the sensor. Here's an example of what that looks like. These are emissions measured over 1 year from this digestate storage lagoon, actually an earthen storage. We can see this, over the summer, the emissions from the digestate increase, and in the winter, they decrease. But we can also see when new feedstocks were added, there was an increase in the digestate emissions too. Here's another study where we looked at emissions from the storage tank before the addition, before the digester was built for 1 year. We have the gray bars. And then the year after the digester was built, we have the pink bars. And overall, we see 85% emission reduction from this farm after adding the biodigester. So again, a big reduction, even bigger at the farm scale than we saw in the lab. Another study, we looked at nutrient recovery systems, and I'll describe how this works. This is a farm with a biodigester, and the digestate goes into this system, comes in through a press, and then a screw press separates the bedding material, and then the liquid goes into this dissolved air flotation system, which isolates the solids, floats them to the surface. Those solids get separated as what they call a cake, and that's used for fertilizer. And the liquid fraction finally goes into a storage. So that liquid digestate is what we measured. And we took samples from all parts of the system. And here's what we saw. Here's the IPCC default value for methane potential of around 240 milliliters of methane per gram of volatile solids. With the anaerobic digestion system, the biodigester, we see a reduction at this farm of about half. After the screw press, we see another reduction because solids are removed. And finally, after the nutrient recovery system, the emissions of methane are zero. And in the real world, with the on-farm measurements, we see a bit higher than zero because of some old carbon left at the bottom of the lagoons. But we don't need to go necessarily to a nutrient recovery system to reduce methane. We can also achieve reductions using acidification. What we did in a number of studies is we added a small amount of sulfuric acid one time to the manure. And we saw that it decreased the pH a little bit, and it resulted in an 85%, if we choose the appropriate rate of about 1.25 grams of sulfuric acid per liter, we can get 85% methane reduction and 20% ammonia emission reduction. This could be done for digestate, but there are still some technical things that need to be solved for doing it on farm. So those were some studies about methane primarily, and we also looked using the same techniques at emissions of ammonia. We have 4 farms that we studied. The first farm here in the top left had no biodigester and no screw press. It was a conventional farm system, and the liquid manure had a very thick covering of solid material from the bedding. There was very little ammonia emissions because of that crust. Then we have a farm that had no biodigester, but it did have a screw press. So there's less solids and less crust, and then the ammonia emissions is higher. Next, we have a farm that has a biodigester and no screw press. Has a little bit of surface crust, but because of the pH and the increased ammonium concentration, we still have higher ammonia emissions. And finally, a biodigester that also has a screw press. There's no crust on the surface, and we have the higher pH, the higher ammonium concentration in the in the digestate, and so we have the highest potential for ammonia emissions. And if we look at the same data in relation to the time of day, we see, again, in the same order, the farm with no special practices has the lowest peak emissions in the afternoon. The farm that has the screw press has higher peak emissions, a bit more than 1 gram per meter squared per hour. The farm with the biodigester or anaerobic digester has about 2 grams per hour in the middle of the day. And then the farm with the digester and the screw press has the highest, sometimes as much as 3 grams per meter squared per hour. And we can see similarly the relationship to wind speed is very strong when we have the biodigesters and less strong when we have no biodigester. So moving from the storage to the field now, we did a number of studies looking at ammonia and nitrous oxide from field applications of digestate. For ammonia, we used flow-through wind tunnels. These have a fan that covers a 1 meter squared area of soil. We put the digestate on the soil, turn on the fan, and we sample the air coming in, and we sample the air going out. And using a mass balance, we determine the emission rate each sampling period. So here we see 2 curves over time. Most of the ammonia is emitted very quickly. And we see for the manure, the dairy manure, it increases and then stabilizes. For the digestate, it increases very high and then continues to increase. This was in the late spring when it was quite warm. We see higher emissions from the digestate than the manure on a surface area basis. In the fall, when it was very cold, we see the same pattern. Digestate is higher than manure, but it's a much slower process because of the temperature. And we compared these measurements, the circles, against a model called ALFAM, and we see somewhat good agreement for the warmer season. And so, because of the pH being higher and the amount of total ammonium nitrogen in the digestate being higher, we get a higher amount of ammonia loss per cubic meter of manure. But if we were to adjust the digestate application rate based on the ammonium content, then we could have a similar amount of emissions. So that's something to keep in mind when applying ammonium, is to adjust the application rate in the digestate. Here's another study, another part of the study where we looked at the nitrous oxide emissions from manure and from digestate and from fertilizer. We use static chambers all year, every week, throughout the whole year, including the winter time. And the manure was and digestate was applied in the fall, before the winter, or in the spring, before the growing season. And what we see is the key times when emissions occur are in the spring when the snow is melting and the ice is melting, and after the application at the beginning of the growing season. So we characterize that over several years, applying digestate in fall or spring, as well as manure in fall or spring, and compared it to fertilizer. And what we found was that the difference between digestate and manure depends on the year and depends on the soil type. So we had one field with a sandy loam texture, another field with a clay texture, and in the sandy loam field, the digestate had higher emissions than manure and also somewhat higher than fertilizer. But in the clay texture, the emissions from digestate were less than the fertilizer or similar to the fertilizer. It also depends on the time when the digestate was applied, if it was applied before the growing season or if it was applied in the fall. So overall, the facility scale emissions are important to consider. There's potential for leakage, but with appropriate design of the system, we can see quite low methane losses. The storage of digestate is an important source of methane, but it is much less than manure. And with additional treatment through a screw press or nutrient recovery or perhaps acidification, the methane emissions from the digestate can be very close to zero. And it's possible usually to have higher ammonia emissions from digestate, but those can also be mitigated through pH modification. And in the field, there's a high risk of increased ammonia loss with digestate that could be managed by injecting the manure into the soil and by adjusting the application of rate to take into account the TAN concentration of the digestate. So that means apply based on the nitrogen, the ammonium nitrogen content, rather than just the volume. And depending on the climate and the soil type, the nitrous oxide emissions could be less than fertilizer, but it's something that probably needs local studies to understand. And with that, thank you very much. Have a nice day.